Hello everyone. First and foremost, thank you for DPDK team for selecting our talk so that we can come here and share our learnings and findings that we did while working on container-based applications. Myself Vipin, and with me I have my colleague Shiva with me. We both are working in AMD and it has been 2.5 years working together. That's a quick intro about us. So, number one, a small primer. Container-based solutions is not what you run on. Container-based application is not what you run on your host or in your virtual machine. Why do I make that primer, or why do I make that statement? Is because what we got to see is people come, end users come, or the customers come, they deploy their standard application that was created on a bare metal. They take it and put it in a container. They come back and tell us, hey, we have throughput issue. Whatever I was getting like 50 gig and all, now I'm getting only 48 gig. When I see packet burst, I see packet drops coming at the tail end. Whatever was taking like 60 microseconds to process in a function, it is taking like 75, 80 microseconds and all. I get tail latencies coming in. I sometimes see it is fluctuating all the way up to 150 microseconds and all. Now, I try to write some metadata. I try to write logs into file and all. None of these things are working properly. These are the common complaints that we got to see from when any customer trying to deploy inside a container, especially with DPDK, VPP and all. Now, we tried certain things to work with them, like using counters, using flame graph, func latency from IO visor and all, trying to identify where the problem is or why this problem occurs. Most of the times, we do not get answer. We'll talk about 3 or 4 such use cases where we face such problems, and we'll try to share with all what we learned from it, how we ended up debugging those things, what we need to change within DPDK or within the documentation ecosystem of DPDK to address these problems. That is the main agenda that we target for. So I repeat this again. Our main focus is to share that 3-4 different use cases where we understood or seen these problems, what were the symptoms or byproducts of it, what was the real cause of the problems, and how we mitigated it. That is what we want to share in our session today. Shiva?
Okay. So what we have been, I will try to summarize some of the problems or what we hear from customers in terms of challenges towards scalable performance and so on. So in that regard, basically, as we all know, with the growing demands, right? So we keep adding up more resources in terms of CPU and things like that. But what we expect is basically performance increases linearly with more number of cores or more number of servers and so on, right? So that's what the goal is. But again, at the same time, things have been changing quite a bit. So at least people, initially, all the applications that were built on top of DPDK were deployed on bare metal servers. And wherein you have the infrastructure basically, in terms of whether it is IOMMU or whether it is device pass-through and things like that. It's good, but and then slowly it got evolved into virtualized environment wherein you have virtualized memory manager to provide the infrastructure, and basically we have one or more VMs running on each server. Of late, basically, and things have been more cloud native specific in the sense things are running into containers and microservices. So what it means is basically what we initially think of I have an application which is built to run at a single service on a specific server. It got into virtual machines where you have one or more virtual machines running on one server, and then for scalability you need to have more servers running in a cluster. But that things have also been changed into you have hundreds and thousands of containers running on each machine, and then you have basically a number of such servers in a cluster. The scale have increased quite a bit, and but again at the same time it has what customers deploy built applications built using DPDK or non-DPDK. what they're expecting is they have a unified application which runs across these different deployment models, but they wanted deterministic performance to meet the KPIs, which is going to be challenging because, like, when you move from one environment to the other environment, like things, like there is a bit in the infrastructure, whether it comes to the security aspects, privileged execution and so on. So that's where, like, it brings additional challenges in terms of observability and in terms of CPU profiling, tracing, and so on. So we'll discuss some of those challenges, what we have experienced, and what can be done better in the DPDK community, and also, from an infrastructure standpoint.
Just to touch base, what we are trying to say is, an application that is written for a bare metal, you don't have any restriction. You write it, you assume it runs. If you have CPU, if you have memory, it runs beautifully, no problem. But once you move into container, that's a least privilege area where your quotas, dynamic scheduling, multiple container instances and multiple pods would be running together, which would be using your same CPU thread resources and all. That is the real cause of your problems. And these use cases that we are going to talk about will give you more clarity.
So the first model, again, in the 5G space, is about core functions, it could be UPF or other functions. So wherein you have basically a standard model, again a pipeline model wherein you have n number of worker stages, each could be performing a single function, and then you have a distributor, you have a collector basically to distribute among these workers. And then, you have a collector basically to just maintain the ordering and so on before they're getting transmitted out. So this is good. Again, the same model, if you look from a container standpoint, so you have basically multiple pods running basically one or more stages of these functions. So from bare metal to container, what it means is whatever you are running on a fixed set of CPUs, you're going to basically put it on a pod, which has where you're not completely bounded to a specific set of CPUs and so on. The second model is again similar to that, but it's a run to completion model wherein for scalability you will add more number of VFs. So each VF could be serving one or set of cores. Again, you'll have other challenges here in terms of, so again, one of the things that we discussed earlier is about basically how you can ensure the dynamic load balancing challenges that you'll face, between different subscribers, things like that.
So in the first use case, what the customer came from the bare metal environment. For him or her, what they did was they take 16 or 32 CPU threads. The 100 gig NIC or the 400 gig NIC was placed on top of it. They know it is fixed number of things. But when they moved to the container environment, they wanted to run multiple instances of it. That is 32 core container, 32 core container. Each would be processing 200 gig each. That was the first model. And they were expecting they would get, oh, I just have to add one more container if I want to do the next 200 gig. They were expecting a linear scaling. They did not see any linear scaling. Then they went and experimented in this model. Okay, maybe the scaling problem was because of the, can you go back? Because of the packet distributor container they had. Maybe it is not reading enough packets and distributing it to container 1, container 2, container 3 to do the work. They thought that was a problem. So they switched over to use case model 2, wherein which using the hardware, they bifurcated the traffic. They said IP address 11.11.11 till 12.12 go to VF1, IP address 13.13.13 go to VF2, etc. They partitioned it. They tried running the same model, 32 core container with each VF supporting it. Still in that model also, they did not get performance. They were getting varying jitters. They were getting packet drops and all. Now, third.
So the third use case is in the, it's about the RAN deployments, wherein, so it's more emphasis is on latency than throughput. So the other challenge is for example, if you are actually deploying it on a, in a container model, so you have basically, you expect functions to be performed in a specific amount of time. But like, what if there is a contention, like, if you have hyperthreading enabled, like there will be contention between the hyperthreads, and then you will not, like, it will take a few more extra cycles than what you are expecting. The second thing is, so like, you have basically functions which require like, locking kind of thing. And the amount of cycles that, like, you might take, like, to get this locking, acquire and release, that's going to vary based on, like, the location of the pod and things like that. So the other function is about basically, like, the sanity of your memory cache and so on. So based on that as well, like, you will see that in increase in the, like, cycles, like, based on your cache state and things like that.
So just to explain this little more. So in the lab, they put a VRAN, virtual RAN, with 16 threads doing 9-cell scenario. What they found out, everything runs beautifully. Just like bare metal, you're getting all the performance, you're meeting all the KPIs and all. But as soon as they deployed the next container, which is 16 threads, they started to see fluctuation in terms of timing. One very simple example is, in your L1 layer of your VRAN, there is an area wherein which the IQ samples are extracted by multiple threads, and you will be processing the data. Now, after each IQ payload is getting processed, it will be reused again. We don't want to do free alloc, we don't want to do that. So it was reused again. So before reuse, they used to call a memset function, which allowed to go and write some dummy data there, like zeros or 1111 or a certain pattern and all. Now that particular function, which cleans up the buffer and helps to reuse, when one container instance of 16 threads were running, it was taking around 15 microseconds. But when the second instance of it was deployed, sometimes it takes 120 microseconds. Sometimes there is no problem. So this sometimes unpredictability was a problem in VRAN scenario when they were deploying with inside the container. Same piece of code, no changes, same set of libraries, same set of functionality, but sometimes it runs slow. Sometimes everything is perfect. This is another use case from another customer wherein which they were getting ER span data or mirror traffic. From the mirror traffic, they were correlating and creating a simple logic wherein which they can say, oh, I got 10 flows. For example, how many users are currently using YouTube? How many users are currently using the audio call? For that correlation, they wrote an application which was running on a bare metal. They took this bare metal application, they put it inside a container. It worked nicely. Now that can process up to 25 gig of traffic. Now in order to get a linear scaling, they went and started deploying 4 instances of it on the same server. Now what started to happen is that there is no CPU problem. There is no memory bottleneck. But somehow the data that gets written or updated into the NVMe disks were running slow. Nobody knew. We were not able to figure it out initially what was going wrong. But basically it was stalling. Okay, so what we thought, maybe we'll go to the DPDK documentation, trying to figure out if there is any clues there. So based on the DPDK documentation, these are the normal things that they talk about, how to get good performance. If you go to certain vendor-specific performance report and all, they give you some grub settings, they give you some BIOS settings and all. But most of the time, there is not much documentation related to container or container debugging. The container information that we have today in DPDK is about how to run in a non-sudo format or least privilege format, how to run a DPDK application in a container. That is only what the DPDK documentation as of today was encapsulating. So then we use the Linux tools like perf, IO-Visor, func latency and all. We started to profile. Now here comes the funny part. If you take Intel vendor, they have something called as PEPS, Precision Event-Based Sampling. If you look at AMD, there is instruction-based sampling in perf. If you look at ARM, they also have something like an instruction-based sampling and all. But for these to work, you have certain kernel dependency. Suppose your host OS is 6.2 kernel, but your container is deployed with a package of 5.2 or 5.4. These things would not work. So whatever we wanted to gather with regard to precision-based sampling or instruction-based sampling, none of these things worked. So we are at loss. But we know the same application, if you run it on the host, for the memory part, we can do C2C, false sharing, we can do all those perf analysis. We can see how many write combining are happening, which is reducing the amount of tokens from the backend engine. We can go and look how many software prefetches were made, how many hardware prefetches for the strided data are made. All these data we could have collected. But none of these data, when again, depending upon what container and container libraries and other things you deploy, none of these data were available or visible to us. So the notion of using perf inside a container was a no-go. Now, more importantly, if you don't have the right privileges inside the container, that is, if you don't have the admin privileges inside the container, you could not even run perf also. So perf is out of question. We were not able to use perf. Next. So then we thought we'll do a static code analysis. Like we will try to figure out how many code blotting is happening because of inlining, how many LTO related, non-LTO related problems came, how many cache misses were there and all. We thought of going and using. So we thought, hey, I will put a small vendor specific like observability into there, either using IO Visor or eBPF, or by directly using vendor specific calls. I will do some tracing and I'll try to figure out. Now, here is a problem. We go to our Ubuntu and we do DPDK apt install. If we do, the libraries that you get there, that is built there, is different from the library that you get built from the Red Hat. My friend Shiva in the last DPDK summit in Dublin was talking about the impact of packaging. If you have a package that is built with certain specific flags, it is not the same performance on vendor A, vendor B, inside vendor A itself for processor A, processor B. We'll talk about why it is not the same too, little down the line too. So what we understood is your compiler makes an impact for your library, whether it is DPDK or non-DPDK application. Your flags that is used to build the libraries also affects it. Now, your optimizations and other things that is added to the library affects it. If you are using any custom library or handwritten optimizations, for example, there's a code path. If I have FP16 support on a specific vendor CPU, and if I don't have a FP16 support, it's like a if-else or a function pointer. So each time when you do that lookup or dynamic checking and all, you're wasting cycles. So remember the mindset of the customer. I have a generic code that is written. I just use a compiler. I create a binary. I go and deploy it on any container. It can be from vendor A, vendor B. It can be ARM, PowerPC, x86. It doesn't matter. I just cross compile and put it. It should run. So inside, let's take AMD as a vendor. Inside AMD, we have CPU cores which has larger iCache, smaller iCache, larger number of TLB and all. So the same piece of code behaves differently. So all this hardware and software feature affects your performance or degradation in your throughput. Figuring these things out were not easy because the observability that we had inside the container were limited.
So seeing all this, right, like, what was the real cause of these things, right? So we tried to list down some of the root causes of like, what we are seeing, like, when it comes to the container deployments or things like that. So the first thing is about like, so when you're running a container, again, like, again, I'm not talking about a privileged container. I'm talking about non-privileged general container. Is you have access, limited access to the various resources, whether it could be CPU resources or whether it is CPU, let's say perf unit and things like that. So you have limited access, file systems, everything, right? The second thing is whatever you're assuming, like, basically like library versions and compiler versions, there is a version mismatch when they're actually getting deployed and running in a container. The third thing is, like, you need to basically, like, you need to apply specific patches if you're, like, if you're, whatever the patches that you think are running, you need, those patches are missing. So basically the libraries are something that, like, it's not the same that you think it is running. The other thing is, so there is a, There is a content, again, like, based on the, let's say, if you're deploying on different x86 servers, right? So based on the type of the architecture, again, like, the performance will vary. So I'm trying to list here a split cache architecture. So wherein, like, if the pod is entirely deployed completely on a specific LLC domain, right? So the performance will be, let's say, X. The same pod, like when it is deployed at a different instance between X and A and B, so the performance is going to vary because the cycles it takes to, like, for the data access and things like that will vary. So there has to be some kind of awareness for the orchestrator, things like that, when it tries to place the pod. So some kind of intelligent mechanism to make sure that it gets placed along with the socket awareness, right? About the cache awareness also.
So what Shiva is trying to highlight here is, if you look at the figure right here, you see two core complexes in blue color, 1 and 2, which shares the same last level cache. So if you have two threads, assume that it is running in a pipeline model. Stage 1 will do your IPsec and reassembly and all. Stage 2 will do your natting and etc. So if it is within inside the same LLC domain, the data is available either in the L2 or in your last level L3 cache. But if you put two threads, which you don't have a control when you're sitting inside a container, it all depends upon your infrastructure provider. If you're sitting across two last level cache domains, then the probe request has to go through one domain to the next domain. Similarly, just like CPU NUMA or this last level cache splitting that we talked about, there is also a domain. Within one physical CPU socket itself, there is an internal partitioning of your PCI bus, your memory channels, and all. So the closer you are to the memory channel and the PCI bus, the faster you get. But these things are visible when you are sitting on a host or bare metal or a dedicated VM. But when you are inside a container, depending upon how your container D decides where the resources are going to be placed, these things would vary. So you have software problem, your version problem, now you have hardware problem also. These constituted to all the different types of jitters, latencies, or that unpredicted random drops I was talking about.
Rather, like, it's a hardware awareness problem.
That's a nicer way to say it. Since the container does not know about which DPDK thread 1 is from box 1 or domain A, DPDK thread 2 is from domain B, you can tell it is a hardware problem. But this visibility, this telemetry is not available in our current library or current systems.
Yeah. So in addition to that, basically, like, we talk about RAN use case, like about deterministic latency. Imagine like the pod, like, or two pods are getting scheduled on two hyperthreads. And in which case, like, there is instance where they are deployed on two hyperthreads, instance 2, they are deployed on two physical CPUs. So again, the latency is going to change as well. So that is something that...
the very good example is that zero packet drop for 600 byte payload on a UPF core, we were able to do that on 24 CPU threads. But the same thing, when you put it inside hyper-threaded scenario, we need 32 thread. So if your infrastructure or the pod man is able to identify, oh, already I have deployed this container one, which is UPF, on ABCD, I will not use that SMT thread, then you get that 24, 24, 24 scaling. If that intelligence is not there in the pod manager or infrastructure manager, then all these kind of abnormalities you will start to see. This is what Shiva was mentioning earlier about hardware level abstraction or hardware level awareness is missing.
So the other thing is, right, so I mean, DPDK, we talk a lot about CPU isolation, things like that. But when it comes to the, let's say, the Kubernetes or any other orchestrators, right, there is nothing like CPU isolation currently supported. So even if the pod is a guaranteed pod, right, or pod with guaranteed QoS, still that CPU isolation is something that could, again, it depends on the Linux scheduler to make sure that it doesn't schedule anything. So that is something to keep a note of.
Let me explain that. One telecom vendor, what they did is that they wanted to get best out of the hardware. So what they did, They put real-time Linux on the host OS. They used WindRiver container system to orchestrate and create it. And they said, since we know this SMT problem, the partitioning problem and all, we will create a simple init script, which is like a Perl or a Python script, which will go and query the hardware based on the subNUMA sectioning. It will say core 0 to 31 is on NUMA 1. Core 32 to 63 is on NUMA 2. And we will then just copy this small text file into the temp folder of each container that we start. So if you're container 1, you will pick up file 1. If you're container 2, based on your ID, you will take file 2. That means that you will take specific DPDK course only. You will take DPDK course from 0 to 31. You will take DPDK course from 32 to 63. Like that, they did that activity. Even there, they also face the same problem. Why? Because just like in the earlier figure, where you had CPU core complex sharing the same LLC, different versions, different SKU number had different thing. We tried to fix this actually by putting a patch series into our DPDK CPU layout.python script. But it was met back with certain things. Thomas can explain that. But that is where we were trying to fix things so that these kind of observability, these kind of information is at least seen inside the container.
So what we learned from these exercises is, right, how we can at least troubleshoot some of these issues is, so what we started off with profiling the application to make sure optimize it on bare metal and subsequently deploy it on the pods to see the infrastructure challenges. So whether it is in terms of functional latency, module level latency or library things like that. And the other things is, again, things that we are looking at is basically how can we bring that CPU isolation to the orchestrator level, like adding custom plugins and so on. And extend the existing DPDK telemetry infrastructure, at least for a better observability, because that is something that is going to be more critical, as we start to migrate towards the cloud native deployments. And one of the things that we are looking at is basically the eBPF, hooks, runtime hooks, basically at different points to get the perf telemetry data, at least when you are deploying it as a debug pod, running with the privilege levels and so on.
So what we are trying to tell is, today if we go to DPDK and look at the telemetry part, you can get RX stats, TX stats from the NIC. Maybe you will get crypto stats, statistics and all. These are not enough to tell what is going wrong inside a container application. We need to give not just telemetry in terms of statistics, we need to give telemetry in terms of where the threads are running, how much is the occupancy, because please remember, the scheduler that is running outside the container determines the CPU quota. The default setting might be 90%, and all. So it is not like your bare metal isol CPU and all, number one. Number two, inside the container, the libc libraries and other things that you might be using is of older version, which might be impacting your performance and all. So you need to figure out a mechanism which can extract and tell you what are the different versions that is getting missed out and all. We need to have some kind of common agreement. We, as a vendor agnostic way of looking at the problems, because on the actual deployments, you would not get a debug container. You would not get access to a debug container where you can run perf and other things and all. So how, using the telemetry infrastructure, how you can expose it? Fourth and last point is, 2 years back, we presented an idea of using eBPF hooks in DPDK layer to go and add, query, get and all. Ultimately, we repurposed that to debug these problems inside container. These were our learnings when we were debugging inside containers for DPDK, VPP and all. Thank you.
Any questions at all of these gentlemen? Okay.
Thanks all.
Thank you.
Oh, you do have a question over here.
Okay. There's a question.
So Vipin, as you mentioned one of the slide that you use the perf application and that is not going to help because you are running it within the container.
No, the container that was used did not have privileges to make use of the PEPs from Intel or AMD's IBS or ARM's IBS.
Agree.
If you have a container with the privileges, yes, perf works. But the question is, now to analyze that, like perf raw sample capture and all, you need to take it outside that machine. Then you need privileges to take it outside too. So all it depends upon how your container is. It's not that it doesn't work, it works. It depends upon the privileges given to that environment.
No, actually my question is not complete.
Okay.
I fully agree that when you run the perf within a container, it will give the local information only and your use case is to run the multiple container, right?
Correct.
On the main host OS, for example.
Correct.
So, then if you're running the container, for debugging purpose I'm saying, if you're running a container, let's say on a particular core, right? You are getting a good performance of that container, right? When you can try to run that container on multiple cores, then you'll see, okay, everything is stable, right? And you are getting same performance, like say 100G or something when you're running on a different core. So there is no core limitation,
correct,
right? Cluster limitation or anything else. But when you are launching multiple thread, obviously there is no expected gain, right? So if you run the perf application on the main host, because all the containers is nothing like a different process, right? For the main host. So if you run the perf there, you can see L2 or L3 level cache misses if happening due to congestion or running multiple.
Absolutely
containers.
true. That is where when we requested one of the customers, what they did is they ran perf. Let's say the containers were using core 32 to 63. They ran perf record on core 32 63 on the host side. What ultimately came out by stack collapsing it, what ultimately came is perf ticks scheduler only, because it does not give you the it does not give you the pointer or the dwarf instructions of what is running inside the container. It just gives you ticks and numbers and all. Now, how do you correlate the L2 miss is from this particular module? Like if you have a pipeline stage 1, stage 2, how do you correlate that? That information is missing. You will just get a generic view. Oh, I got L2 miss, I got L3 miss. That's it. It does not give you the visibility where the problem is.
I think you can, or you may.
We tried.
If you are running perf top command.
We tried perf top. We tried everything. I can show you. I have other slide deck as backup, which can clearly show it.
No
it does not work.
Okay.
Yeah, but yes, that was a good idea. We tried that too, but the problem was there.
And we should also account the isolation of the core, whether you have isolated the core or not. That is a part of debugging.
Okay, see, that is where if you go to container D or K8, there is a plugin, new relic or NR plugins. By default, it does not care about isol CPU and all. Your Linux scheduler, if you tell XYZ, it just checks the quota. Did you get 80% of the quota? Done. Switch over and run the next container on top of the same CPU core. Isolate CPUs are not at all taken. The isolate CPU are only taken in the NRI plugins, and that too also for core and memory. That is one ongoing work. What I believe Intel started 2.5 years back. AMD is adding for chiplet based. That is helpful for any chiplet or split LLC. That is helpful. Thank you.